So it's a bit computational. Okay, I was just looking at some of the books and things. Yeah. Yeah. So we would want to show basically here we would just write the two facts, right? Fact number one is, so obviously throughout n is bigger than 5, okay, and n is a normal subgroup an, okay, and n contains a 3 cycle, and obviously without loss of generality 1 2 3. Okay, now can we just quickly help me to show that it contains all 3 cycles? That should not be difficult. This part, show that n contains all 3 cycles. So you have to just conjugate this by even permutations, right? This one I think is easy. I have not tried to look this one. So let's say that there is another permutation I1, there's another 3 cycle I1, I2, I3. So how do you go from here to there? Okay, by some conjugation, and that conjugation has to come from the even permutations, right? Yeah, this should not be difficult. So if you are conjugating by this sigma, then what should happen, right? If you're conjugating by sigma, then what will this become? Right? So as we saw this last day, right? This is an application of the idea of last day. I suppose this happens, right? Yeah. Okay. Yes. Right. So then you just want that sigma 1 is equal to I1, right? Sigma 2 is equal to I2, and sigma 3 is equal to I3. Correct? So this is what you want. And other options are free to you. What sigma does to the other elements is free to you. So can we now claim that sigma is that we can choose an even permutation that will do this? Right? So we want to choose sigma in an with these properties. That will do the job. Yeah, even to choose this to be even, you can do something like, maybe if I write sigma like 1 goes to I1 and 2 goes to I2, I'm keeping some space there, 3 goes to I3. As we said, that sigma may do anything to other permutations. That gives us the options to choose, and so, but we have to choose so that it's in an. Right. So I think it is easy. We can make it short. We can just do this, and yeah, I have to choose something here. I mean, I'm not spending like on this. I'm choosing it like this because I can do it. I just need to make sure that This last one is so the point is that I can choose anything here, but I should try to not use more than 5 elements. Yeah. That would be better, because then then my proof will work in A5 also. So yeah, this works, right? I mean, here I am assuming that I1 is not equal to 2, and it's not equal to I2. That is okay, that is given already, but it is not equal to 2. If it is equal to 2, then it's probably even easier. Then it's even easier. Yeah. So this will do the job, right? This is in AN. This is an even permutation, and this does the job. So this is the proof of just the simple part. This is the basically based on the principles, right? Finding the conjugacy classes in Sn. Okay. Right. So yeah, from here in my mind arises one question. That if you're looking at sigma and tau, which are in AN, and are conjugates in Sn, then are they conjugates in AN? This is something that you can think about. Okay, so you see what I'm trying to say. I'm trying to say that the first statement is that they are conjugate in Sn, which means that there is a permutation sigma 1, right? There is a permutation sigma 1 such that this is equal to tau, right, in Sn, which means that tau 1 is sigma 1 is in Sn. Okay, then you want to show that sigma 1 can be chosen, can be chosen in AN. If you can prove this, then you don't have to even, if this statement, if you prove, then you don't have to prove these things, because you know that these two are conjugates in Sn that we already saw. But then you would want to show their this lemma would imply this, but I am not sure. Okay, I am not sure if this is correct. Yeah, let's not think about it. Let's not think about it right now. We can think about it later, because AN is a special subgroup. It's a large subgroup, the largest possible subgroup. Okay, so you can note it and try it, and please tell me. And these things you can actually help me with, because I mean anything, but these things are not very difficult, right? Basically, they are based on calculations, but then you can go a long way in these calculations. Yeah. So, anyways, let's erase this. So this is done. But then we want to basically let's clear the whole thing and go to the main thing. Yeah. We want to show that every normal subgroup. Yeah. I think someone's mic is on, and yeah, you can turn it off maybe. Or you have to use I mean, when you speak, you turn it on. Because if you're not using a earphone, I think I don't, not technically, I don't know properly, but yeah, maybe that's why I can hear my voice. Yeah. But yeah, when you speak, you should certainly turn it on. And if you're using a microphone, then I think there's not a problem. Yeah. Anyways, I don't. Okay, let's continue. So every normal subgroup of this is the hard part, I think. N in AN, okay, has a 3 cycle. Okay, So anyone has got anything here? No? So this one, let's see. So I was trying a few things, but unfortunately they did not work. So I'll not talk about them. But let's see what does work. So remember, our goal is to prove this and then to also consult the proof in Damit and Foote and see the ideas present there. Yeah. The proof of this theorem is nice and the theorem is nice, but also the ideas that are present are also sort of very nice. Anyway, let me not delay this. Yeah. Right. So somehow the ideas here come from constructing commutators. Just a name I'm giving. I mean, just the name, this is a definition, but commutators. And so, yeah. Yeah. I mean, in fact, I should have not missed it because commutators are sort of very interesting objects. Okay. Even, yeah, they are very useful in other things, even in just kind of questions. So, but anyway, let's look at this. So you take this sigma, okay, sigma in n, okay? And let's just write the standard disjoint cycle representation. Okay, so let's imagine that this is the standard disjoint cycle representation. Uh, right. And basically, what you can just do is something like this. No, so this is uh, this is a K1. Want to write it? I mean, I don't know. So it doesn't matter. So yeah, we can put a double index, but yeah, this is the disjoint cycle representation. Okay, so disjoint. So now somehow from here we need to, get a 3 cycle somehow. So how does that work? Yeah, and there is this thing that if K1 is at least 4, okay, if K1 is at least 4, I don't know about that. Just a minute. Yeah, K1 is at least 4. So that means I will write more things here. Okay. Yeah. Then the idea is to conjugate by something. Okay. So that these are not affected. Okay. So that tau does not affect these things. And then the benefit of that I suppose is that when you do this, then these things are out of the picture, right? That is the idea. But let's execute it. So I mean, let us see. Let's see. So So you want to conjugate it, right? So what is the simplest thing that you conjugate by? What's the simplest thing that we can conjugate by? This, right? That's the simplest thing, right? And again, remember that conjugating, so maybe I will change a few notations. It's not good to call this tau because this is not a transposition. Call it rho. Okay? And our rho is coming here, is this. Okay. Now you see, if you are going to consider, like if you're going to consider this expression, right? This again something that we saw the last day, that this is the same thing as conjugating this first, right? And then conjugating each of the cycles separately, correct? Each of the disjoint cycles. So the conjugation is a very nice operation. You can conjugate each of the cycles separately. That's same as conjugating the product. That's always true. Okay. I mean, in any group, conjugating a product of elements is same as conjugating each of them separately. So that is the good thing which we are going to use. So now you see, so basically this becomes quite interesting, and the disjointness again also plays a role. So there are so many aspects that are coming into play. So let's just call this C2, C3, C right? So yeah. So conjugating this, maybe this should be certain capitals because it's cycles. Maybe C2, C3, CK, and sort of conjugating them. Okay, fine. I'll erase this. Just keeping the main ideas, and the rest you can actually generate. But then you see, this thing will actually be equal to C2, C3, CK. Correct? Because this A1, A2, A3 don't appear in this at all. Don't appear in any of the cycles, correct? They don't appear in any of the cycles, right? So when you conjugate, it doesn't have any effect, right? A1 goes to A2, but A2 is not here, and then you come here. I mean, this is inverse. So A2 goes to A1, and then A1 goes to A2. In this, nothing happens. So you get the same thing, and that's what I was talking about, right? So okay. So this will just be C1, C2, C2, C3, CK. Okay. Now let us think, what will this thing become? Can you say? What will this thing become? The idea is to somehow pull out a 3 cycle. So just calculate it. So this, let's write this. I'm writing it here only. A3, A2, A1. Okay. So what happens? A1 goes to A3, A3 goes to A4. So this becomes A1 goes to A4. Is this correct? Yeah. And again, I mean, if A1 goes to A4, A1 goes to A1 goes to A3, yeah, correct. And then of course this will just be the rest of the cycle, no doubt. But then we should look at the other things where A2 goes to A1 and A1 goes to A2. Okay, so A2 is not there at all, it gets fixed. A3 goes to A2, A2 goes to A3, A3 goes to A1. So A3 goes to A1. I hope this is correct. Okay, but this is not a useful construction, right? A3 goes to A2, right? I did not want this then, right? I mean, I needed a 3 cycle. Okay, let me see what they have done in the thing. Yeah, it's 1 second. Huh? And this is phi 1. Right. So if I'm just conjugating, then finally I'm getting this 1, 2, 4, and I'm getting this sigma back. What is sigma? Yeah, I mean it's the same calculation I'm doing, but somehow I'm not getting that. Yeah. Okay, let's see. Let's go over this. So let's erase this for now. Yeah. So we are considering this. We are considering sigma inverse. Right. We're just considering this. And this looks correct. Okay. And in the rest of the thing, it is just this. Correct. And this thing is not affected. Is this calculation correct? Is there anything wrong? Yeah, there is a small mistake. There is a mistake here. So we know there is a AK, right? This AK goes to A1, but A1 goes to A2. So this is A2. So that is there. So that was wrong. But hmm, no. AK goes to A2, right? But this, I mean, of course, this will again be a 3 cycle, right? So I'm writing something wrong. Yeah, now this is correct. Yes, this is correct, right?
We
Yeah.
have we have taken sigma of different cycles, but do we need to conjugate it with any different cycle than sigma? Like where we are taking the
And
rho, we are
yeah,
taking
uh-huh. We are taking rho to
yeah.
be this.
But rho and sigma are not totally distinct. No?
Yeah, but that is not needed. That is not needed, right? Sigma and rho, if they are disjoint, then it's not useful. That's what happens to the second component. If they are disjoint, like these cycles are disjoint with rho, and so they are not affected. That's another feature, right? Yeah, fine. So we are getting this. Let me just write this again. So this is A1, A4, A5, and then, yeah. It's a slightly tricky, I suppose. We are writing A1, A4, A5, and yeah, then it's just normal AK, and then it was A2, A3, right? Is it correct? A3 goes to A2, A2 goes to A3, A3 goes to, right. This, and then the rest of the permutation is there. C2, C3, CK, right? So, I mean, as you expect, right? When you do something like this, it will not pull out a 3-cycle directly. Okay, it will not pull out a 3-cycle directly. But the main concept comes here, that now if I do sigma inverse, then what happens, right? Now I do sigma inverse, and this is what is called a commutator, right? So if I do sigma inverse, then I have ak minus 1, a3, a2, a1, and of course this is just the inverse of the first cycle, and then these are the inverses of the other cycles, right? And then actually things become simple. Now things will start to simplify. Okay, that this part gets cancelled with this part because it is joint and so on and so on. So that is okay. Now what can we say about this? Here your 3-cycle should pop out. Okay, so a1 goes to ak, ak goes to a2, so a1 goes to a2, then a2 goes to a1, a1 goes to a4, and this. And now you look at a3, a3 goes to a2, and this will again go to a3, right? So it's not a problem. And you see the rest of the things will actually form another cycle, as is obvious, because a4 will go to a3 and a3 will go to, no, what happened? No, not a4, a4 is already there in the cycle, yeah, a5. a5 goes to a4, but a4 will be nice, a4 will go to a5. So that will just form a, you can understand, that form the cycle, right? And what cycle will it form? Okay, that also we need to see, right? Yeah. Right. No. Something is wrong. Sorry. This happens. What happens to a5? Yeah, I'm just saying something by assuming completely. That's completely nonsense. Yeah. a5 goes to a4, right? And a4 goes to a5. So it's fixed. And everything will be fixed, in fact. Now I can say this based on some evidence, right? a6 goes to a5, but a5 goes to a6 because I mean the rest of the portion is inverse, and that's so your 3-cycle pops out. Okay. Yeah. So right, this is the thing. This is the thing. Okay. So you should just repeat this argument, and you should think about this. Okay. That how this is working. Okay. See, one of the key features that we are using is that this has length more than 3. And that kind of trick, you can call it a trick, but that's like a degree of freedom, right? An extra dimension, right? An extra degree of freedom allows you to construct more and more things. Okay. So that we are using, and then we are getting, and you can work it out for just forget this and work it out and see. But this is called a commutator of sigma and tau, which is a very, very nice thing which we can talk about later. But you see, this was only one case in which the largest cycle has length 3, has length at least 4. But then the rest of the cases, I suppose, are not very difficult, but let's have a look at them. So the other case would be, maybe I'll just do it on the next page. Yeah. So today we'll not go into the Dummett and foot proof, and that probably I'll leave for you to read and present me if you would like. Okay. I mean, just read and share with me. Now, case 2 would be that if all cycles have length less than 3, I mean, at most 3. Yeah. And I mean, those are some small cases, okay, not very difficult, but we should do them. Yeah. Okay, let me just see. So actually, yeah, actually it's quite some work even from there, right? So, but let's do it. So the next case is that if all cycles in N, of course, have length less than or equal to 3, and at least 2 cycles and at least 2 have length 3. Wait, what happened? Oh, no. Not like that. Yeah, not in N. In sigma. That was our permutation, right? Has sigma have length less than or equal to 3, and at least 2 have length equal to 3. I mean, better to draw. So what we are saying is this is the disjoint cycle representation. What we are saying is something like this, and the rest of the cycles have length less than or equal to 3. So as usual, the rest of the cycles will not really matter. They will sort of conjugate out when you apply the commutator. Okay. So the idea would be to somehow from here you need to somehow get a 3 cycle, right? From somehow you need to get a 3 cycle. And this is actually one of the cases which I was considering, but of course I was not able to do because I was not able to do. Okay, but let's see how they do it. So that is the idea. So you understand, right? This is the idea. Okay. Yeah, but I suppose now that we understand the idea of the previous proof, if we just apply it, then it should just work. And so the idea here is to apply this 1 to 4. Okay, 1 to 4. Yeah, I mean, this is just to me it's a trick, but let's see so far what happens. So when you do this, somehow the cycles will mix up. Okay, and yeah. So what happens? Let's write it first. So 1 goes to 4, 4 goes to 5, so 1 goes to 5. Okay, 5 goes to 6, 5 goes to 6, and 6 goes to 4, 4 goes to 1, so this is a 3 cycle. And now what happens to 2? 2 goes to 1, 1 goes to 2, 2 goes to 4, so 2 goes to 4, right? 4 goes to 2, 2 goes to 3, and so we get this, correct? Yeah. Right, so I should have written it, I can write it better, but maybe we can write this, and then we are doing 1 to 4 and 1 to 4 inverse, correct? Yeah, then we are getting this, but this doesn't help me, right? If I just I don't know. I mean, we have to, what do you have to do from here is you have to just check. Okay, what you have to do is just check. So you take this and then you have to multiply it with the inverse of, that's what we have been doing, right? You multiply it by sigma inverse, take the commutator. This construction is like a piece of construction which is very comes, yeah. So if you sort of, it comes because it gets rid of the rest of the parts, so you get a small part. The degree of non-commutativity of this and this, sort of what this is measuring. This, if this and this was commuting, then this would give you identity, right? So you can see that. That's why it's called the commutator. So you multiply it with sigma inverse, and then a 3 cycle should pop out. Okay. Yeah. Okay, so just check it. Yeah, this is checks. And then there are the other degenerate cases. Okay, that when there is no cycle of length, means basically there is at most one cycle of length 3, and or rather exactly one cycle of length 3, and then there is all cycles of length less than 3. But those will actually be smaller cases, and every time you have to basically take that permutation, conjugate it by some natural thing, and then take the commutator, means that multiply by the inverse. Okay, so you have to start with something like this, you have to consider something like this, which is a conjugate, and then you have to multiply with the commutator. Okay. which is sort of a measurement of how non-commutative it is. And that measurement is captured by 3-cycle, which is in the normal subgroup. Okay, it's in the normal subgroup, even though tau is not in the normal subgroup, because this is in the normal subgroup and this is in the normal subgroup, so the product is in the normal subgroup. Okay, so that's the idea. So the proof is a little involved. You can read it. I mean, these proofs are available, but the point is to get the idea and to obviously to find the energy to read it. That's the, I suppose, yeah. But in a way we have completed the proof. This is sort of a non-conceptual proof, and that is why it looks very tiring. But to find a conceptual proof, now what does something becoming conceptual mean? It means that you need a language, you need certain words, and you need certain concepts, right, which will make this theorem sound analogous to something natural, and then this would also sound natural, right? But for that you have to extend your knowledge of the kind of objects you have, kind of examples you have. Right now we don't have, and that's why this looks very strange. Okay, but it's not strange. Yeah, but for that you have to study more maths. And actually I don't know how to make sense of an being yeah, it is related with a few things I know, but I am not quite certain myself. Okay, so yeah, that is a problem. But doing this proof, I also learned a few things. Yeah, so cell, yes. Yeah, and I can give you some homework, but probably let's not do it. Okay, so we'll not do it. Yeah, and so we'll meet on Thursday. So that is so Thursday 8:30 p.m. Right, and that's my regular default meeting with Vaishnavi. So we will do something. I think we were doing that metric space thing, right? Yeah. So we will continue it. Please work out the things which I asked and metric spaces. Then we can do. So maybe yeah, the idea will be to do problems next time. Problems of Kagzor. Whatever is remaining, maybe you have worked out the problems you had last time. And we'll start with this, and then we'll see if we can. But we'll focus on analysis on Thursday. Okay. Is that fine? Okay. Yeah. So this is what we are doing, learning this group theory, and yeah, that's the thing. Yeah. This is how we become better, I hope. All right. Okay, then see you at Thursday, whoever is joining.